Let's try a ratio test on the sum of 1 over n squared. Go ahead and write out all the math and see what ratio you get in the limit, and then think about, does this series converge or not. So pause the video while you do all that and then come on back. Welcome back. So we're going to say an plus 1 over an is 1 over n squared in the bottom here, and in the top 1 over n plus 1 squared. And then do the whole denominator flip thing. So we're going to get n squared over n plus 1 squared, which we could also write as n over n plus 1 squared. And then we'll say, what's the limit of that as n goes to infinity? Well, we could say this is basically infinity over infinity plus 1. Put that in quotes, squared. So that's like a billion over a billion and one, or a trillion over a trillion and one. Two numbers that are very close to each other. When you divide them, you get basically 1. So you get 1 squared, which is 1. And we'll call that L. Does this sum converge? The ratio test, we're not sure yet, but we can apply a p-series test, right? So p-series with p equals 2 says this sum converges. Right, so we didn't have to do the ratio test to know whether the sum converges or not, but we're doing the ratio test to see what it does on a sequence like this, or a series like this. Now let's try the sum of 1 over n. Go ahead and do a ratio test on that, see what happens. Pause the video and come back when you want to check. So an plus 1 over an. So 1 over n in the bottom, fairly straightforward. And 1 over n plus 1. And do the whole flip thing, and you get n over n plus 1. So then we'll take the limit as n goes to infinity, n over n plus 1, and we get infinity over infinity plus 1. Again, not really supposed to write that, but that's sometimes not a bad way of thinking of it. Since the n's are kind of the same order of magnitude here, rather than an n squared in the top and an n cubed in the bottom or something like that. So overall we're getting 1, which we'll call L. And does this sum converge? Well, we know a p-series would use p equals 1, so the sum diverges. This is the harmonic series, famously divergent. So let's wrap up what we saw. Both have L equals 1. This one and that one have L equals 1, but one of the sums converges and one does not. So if we get L equals 1 in the ratio test, can we say for sure that the sum converges? Well, no, because maybe it's this one. If we get L equals 1 in the ratio test, can we say for sure that the sum diverges? Well, no, because maybe it's that one. So overall, L equals 1 in the ratio test means the ratio test is inconclusive. Because there are examples with L equals 1 that converge and examples with L equals 1 that diverge. So L equals 1 is just not enough information to be able to tell the difference between these two things.